So we talked about how resonance hybrid is the weighted average of all the Lewis structures, but how do you know which one is weighted more than the other, right? And so let's say the question asks you which of these structures is the major contributor. And so this is kind of like, this could be for many reasons, right? There could be many reasons why one structure is more of the major contributor than the other. But in this case alone, there are two reasons, right? One of them being that in this one, all the compounds have a full octet, right? So 2, 4, 6, 8 for the oxygen and 2, 4, 6, 8 for the carbon as well. So all the compounds here, all the atoms here have a full octet, but in this one we see that the carbon has 2, 4, 6, so it only has 6 valence electrons when it needs 8 to complete its octet. The oxygen does have 8, so this one's fine, but the carbon isn't. So since this one has both the carbon and oxygen with a full octet, this one would be the major. And also, for another reason, is the fact that if you look at periodic table and you look at the locations of right of these compounds, of these atoms, I mean, right, you have carbon over here and then oxygen over here. Okay, and so we know that on the periodic table, electronegativity, the trend for electronegativity is up and to the right. So as you go higher up and more to the right, you get more electronegative atoms, with the fluorine being the most electronegative. And so we can see that based on this trend, that oxygen is more electronegative than carbon, and so that would mean that the oxygen um, is more likely or wants the charge more than the carbon does, right? And so that is also the other reason why this one's the major, is because the charge is on the more electronegative atom. So that's also another rule to keep in mind when determining major contributor, is the location of the charge. Which atom has it on one structure compared to the other one. Okay, for this compound, draw the resonance structure, use curve arrows to show interconversion, and provide a reasonable resonance hybrid, and determine which of the structures is the major contributor. Okay, and so the way I would start this first is I would draw the lone pairs, any lone pairs on any of the compounds. Okay, so here, right, like I was saying before, with the neutral, oxygen is going to have 4 lone pair electrons, and so we have 2 of these oxygens, right, and so they're each going to have 4 lone pair electrons. And then here we see that the carbon has a negative charge on it, right, a -1 charge. Okay, and we know that for carbon typically, like for example this one, right, carbon here is bonded to the oxygen and it's bonded to 3 hydrogens, so it forms 4 bonds total, and that gives us its natural neutral state, right? And so here let's just calculate the or let's calculate the formal charge, right? And so carbon has 4 valence electrons minus um, the number of non-bonding electrons, which, right, that's what we're trying to determine right now. And we know the formal charge is 1 minus 1/2 of 2, 4, 6. So it's bonded to this carbon, bonded to this carbon, bonded to this hydrogen. So that's going to be 6 total non or bonding electrons, right? And we know that this is going to equal to -1. Okay, and so now we just have to determine what x is, and that tells us how many electrons are in this carbon. And then after that, you could just remember that, right? And so if we were to calculate this, right, the way we would have to be able to get -1 is, first of all, we have this is 3 and this is 4. So 4 minus 3, that's going to be 1. And so 1 minus x is equal to -1. And so that would mean x is equal to 2, right? And so that's how many lone pairs are in the carbon. The number of non-bonding electrons is 2, okay? And so we determined that the carbon has 2 electrons and it's also a negatively charged atom, in this compound. And so that should give you your hint to how the resonance structure should look like. And so without moving any of the atoms around, we're going to want to interconvert into the next resonance structure. And the way I would show this, I would take these lone pair electrons and form a double bond between this carbon and this carbon, right? And then we know that carbon, if we were to just leave it like this carbon is going to have 5 bonds, right? And that's going to give it a positive formal charge, which we don't want, okay? And what we would have to do next is move these electrons right here. So it would give the carbon a negative formal charge, which we don't want, right? A -2 formal charge. And so we would want to have to move one of the bonds here into the oxygen above, and so that's going to move 2 electrons above, right? So if you were to show the interconversion between that, it looks something like this, right? CH3, double bonded, right? Boom, 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 right? This oxygen over here is unchanged, and so is this carbon, okay? And so this would give us the resonance structure for this compound. And we could also check the formal charge for the oxygen that I put the negative sign on, right? So oxygen has 6 valence electrons minus the number of non-bonding electrons, 6, right? Already that's 0 minus 1/2 the number of bonding, which it has 2. So that's just going to equal -1. And it checks out, right? So initially we started with a -1 formal charge for the carbon, and we ended with a -1 formal charge for the oxygen. So that's just a way to check your work after drawing a resonance structure, is to make sure you end up with the same formal charge for the whole compound as you started with. So next, let's determine which of these is the major contributor, right? And also draw the resonance hybrid for that. And so just remember what I said with the resonance hybrid, right? You're going to want to show a dotted line for any bonds that are being formed, okay? So first, just like this, start off by drawing the compound here, right? And so I'm going to just leave one of the bonds to that oxygen, not there yet, and right there. So the right side of the compound is unchanged, so we're not going to have to worry about that too much, right? And so we see that what's happening here is we're forming a double bond between the carbons, and then we're breaking the double bond between the carbon and the oxygen, and we're putting those electrons on the oxygen. And so the best way to show this is to draw a dotted line going from the top over there to over here. And so that's how it would look, how the resonance hybrid would look like for this compound. And then also don't forget to show the partial charges. So we see that carbon goes from negative charge to neutral, so that means it has a partial negative charge. And then the oxygen goes from neutral to negative, so it also has a partial negative charge. And that's the resonance hybrid. And so now let's determine which one is the major contributor. So we see that in both, every atom in the compound has a full octet, right? And so this now goes back to our conversation with electronegativity, right? So we saw that oxygen is more electronegative than carbon, so it's gonna more likely to have the charge than carbon is. And so that tells us that this one right here, with the oxygen having the negative charge being the major contributor. So in terms of difficulty, these resonance structures are, I'd say, not too bad, right? Usually what we've seen so far is only like one or two arrows moving around, right? Moving the electrons around and resulting in only one resonance or another one resonance structure, right? We haven't really seen one that has 3 or even more than that, right? But if you do want to see example problems with more complicated resonance, um, just let me know. But for now, we're going to move on to a different topic. So here you're given these four compounds, and you have a curved arrow in each of the one that's problematic in some way, and you are supposed to explain why. Okay, so first we see that the arrow here is taking this double bond set of electrons and putting it between these two carbons. And so you can go ahead and draw that out and the way it would look like. All right. Okay. So all we're doing, we're moving those two electrons over there. Right. And so here, all that happened was we moved these two electrons and we put them here to form another double bond. And so the result would be that this carbon is now positively charged, doesn't have any lone pairs, and the hydrogen is bonded to the hydrogen here, a carbon here, another carbon here, right? And the problem with this, we also see that now this carbon has 5 bonds, which doesn't make sense at all. And so that's the problem. The carbon has 5 bonds, and the octet is exceeded, right? So now for this one, try and pause the video and try this one on your own with the information you got from this. So here we see a similar problem. Initially, the oxygen um, is neutral, but then when you interconvert, right, you have here okay, and so now we see that the carbon is bonded to two hydrogens, another carbon that's already 3 bonds, and then another double bond to this oxygen, and so the carbon exceeds its octet on carbon. All right, so that's the problem with this one. All right, here we have on the third one the double set of double bond electrons going onto the carbon. So what we end up having is this. Right now, there's a single bond between the carbon and the oxygen. Right. So the oxygen in its neutral, when it's neutral, it has 4 lone pair electrons, which we see here it was neutral. Okay. And so now what happened was you moved one of the bonded electrons between the carbon and the oxygen, and you put both of them into this carbon. So now the once neutral carbon now has a set of lone pair electrons and it's negatively charged, and then uh, the oxygen now has a positive charge. And so the problem with this one is that the charges are in poor places, right? There's no reason for the charges to be this way, and so there's no reason for this structure to form. Now for this last one, and this would be the final example for the video, we see that the bond between these two carbons right here is taken and is made into a double bond with the other carbon, right? So what ends up happening is the problem is that you break the compound, right? You break it into this H3C, C, CH, right? And you have a CH3 as well. So the problem is that the molecule is broken. And so this is different than the other 3 that we saw, but there are multiple reasons as to why the arrows are problematic in this case. So that's it for this video. Thank you for watching, and I hope you learned something.